Okay, so I think I will continue. On every other day this week, apart from today, you only have an hour after the coffee break, which is probably more bearable. Today we have in the program another hour and a half to make up for the missing half hour this morning, because the other piece of bad news is we start at 8:30 every other day this week. We start at 8:30, but at least the final session will only be an hour from Tuesday in the afternoons. What I want to do today in the final session, I want to talk a little bit more formally about time series, some concepts that we should have in mind. I want to then really spend some time with GARCH models, because I'm looking for models that can reproduce some of the stylized facts. And it turns out that the GARCH model is quite simple, but it can reproduce most of those stylized facts that I listed for a one-dimensional time series. So it's quite nice as a model, and we will simulate a GARCH model. We will fit a GARCH model to data and talk about its advantages and disadvantages, and we will use it for volatility estimation and forecasting, and talk about how that relates to simpler methods like exponentially weighted moving average or exponential smoothing volatility forecasting. Because for volatile financial time series, if these are our risk factors and we're trying to model the changes in value of a portfolio over time periods like a week, a month, we have to take into account the volatility. The volatility clustering is still present in weekly and monthly returns, and so it's a feature we should take care of. So, 4.1 Fundamentals of Time Series Analysis. At this point, the course looks a little bit more formal because we've reproduced some of the definitions from the book. But I think particularly because it's late in the afternoon, we don't want to get too bogged down in formalities. So I'll try and give the sense of all of these definitions. We'll spend about half an hour on fundamentals before we get into GARCH and then start simulating and estimating. So R will reappear in approximately half an hour. But to begin with some of the preliminaries of time series analysis. Now, actuaries generally have to learn some time series analysis. I know certainly for the UK professional exams, you need a course in time series analysis, and I've taught it to undergraduates and postgraduate students. And there's a lot about ARMA, there's a lot about stationarity and autocorrelations and ARMA processes, and a little bit about GARCH. And so I'll just do a short tour through some of that classical time series, some of the ideas that we should at least have some understanding of to talk about modeling risk factors, but I will then spend more time with GARCH. Okay, so what's a time series? It's a stochastic process. Beg your pardon. So a stochastic process in general is a family of random variables. I think that appeared in Chapter 1 this morning with some index set, and a time series in particular. This index set is going to be natural numbers or integers for different time points with a sense of ordering in time. So some of the things that appear in these slides, we need to talk about the moments of time series. Time series have mean functions and they have autocovariance functions. And until we've decided our time series is stationary, to be general, we have to first define the mean function as a function of time. But then when we start to talk about stationary, we can simplify this notation. So the mean function is a function of time to begin with. It is just the function that gives the expected values of the time series. And the autocovariance function to begin with is a function of two times, and it gives you the covariance between a random variable in this model at time t and a random variable at time s. So t and s are two times, and in general, these times will be integers. And so mu for the mean function and gamma for the covariance function. So these are the first two moments of a time series. Now, the models we use in practice, whether ARMA models or GARCH models, or GARCH models with ARMA errors, I have to work with the right computer, are generally stationary. We work with stationary models. So this is a concept that, for people who've never done a course in time series, is one of the difficult ones to begin with. But I think, again, a lot of you being trained actuaries will know some of this. There are two concepts of stationary, or two usual concepts of stationary that one looks at. There's a concept of stationary which is defined entirely in terms of these two moments, mu and gamma. And then there's another concept which is about distributions more generally. So a weakly stationary, or a covariant stationary, or a so-called second-order stationary time series, you basically look for three things. To begin with, it should be a process xt where the second moment is finite, or it can't be covariant stationary if it doesn't have a finite second moment. So that's the first thing. But more importantly, the mean function should be a constant. It should be unchanging. And the autocovariance function should be invariant under shifts in the time indexes. So if I look at gamma ts and I shift the times, so I shift t by an amount h and I shift s by an amount h, that should not change the autocovariance, or the covariance between xt and xs. It should be the same as that between xt plus h and xs plus h. So if these three things are satisfied, it's called weakly stationary. Strictly stationary, on the other hand, is about distributions. And strictly stationary means that if I take a series of n random variables in this time series, so I take the random variables at times t1, t2, tn, and I shift all of them, again, let's say I shift them by an amount h, I don't change the multivariate distribution. This little piece of notation, which may crop up in various points in our book, is equality in distribution. So I don't change the joint distribution of these n random variables by doing a simultaneous shift in time. So this concept of a joint distribution, if that's tricky, that comes up tomorrow when we talk about multivariate models. Somehow it's almost impossible to decide the correct order to do time series and multivariate models, possibly the other order. But what's the essence of this? Both types of stationarity, it's the idea that xt behaves the same in any time period. So that's the intuitive idea. It behaves the same in any time period, whether we observe it in the year 2016 or the year 2013, it behaves in some sense the same. Now this, from an economic point of view, this seems nonsensical because everything changes in markets and the volume of trades on markets also changes over time, and the rules change, the institutions change, so everything changes. So the idea that you would have stationary and the same behavior in any era is obviously difficult to defend, certainly over longer periods. But in order to make progress with modeling, it's what we tend to assume, at least over short periods, maybe 4 years or something, or 8 years, we might try and fit a stationary model. Of course, we could have models where there are changes in regime, change point models where we change from one stationary regime to another stationary regime. There are other possibilities. But in general, to make progress, we want to assume stationarity. The two ideas of stationarity, you would think that strict is stronger than weakly. Unfortunately, it's not quite that simple. To be pedantic, strict does not imply weakly stationary. If I just write stationary, you can take it to mean weakly. Strictly stationary does not imply stationary, unfortunately, because we have to take care that the second moment exists, and you can have a strictly stationary time series which is infinite variance. But we don't need that for our purposes, but you can have it. The other way around, you would expect that weak stationary doesn't imply strict, because weak only looks at the first two moments. So third moments, fourth moments, these things are not considered. Now, this line of equations, let's just jump to the punchline. If you have a stationary time series, a stationary one in this first sense, then the autocovariance function, what you can show just by a little bit of manipulation, is that in fact it only really depends on one thing, which is the separation of these two times, the so-called lag. It only depends on the lag h, which is and it's the absolute value of t minus s, because it's an even function. Gamma h and gamma minus h are the same. So for stationary, the autocovariance function becomes a function of the lag. And on these pictures of autocorrelations, we tended to, on the x-axis, we had the lag. So this is the lag h. So the picture here tries to convey the idea. Could this be a stationary time series? This is not financial. I believe this is in Hawaii somewhere, Mauna Loa. Monthly carbon dioxide concentrations. There are two reasons why you'd be unlikely to model that with a stationary time series. The first is there is a systematic growth in whatever we're measuring, CO2 concentration. There's a systematic, almost a deterministic growth. You have a feeling that you could lay some sort of exponential curve through this quite satisfactorily and predict the trend. Moreover, there is a very strict periodicity. There is an annual cycle in CO2 concentration. So there is another deterministic, predictable element in this time series. So whether you look at December observations in the 1950s and March observations in the 1980s, it's clear that these are taken from different distributions. The level's different, and also you're in a different part of the annual cycle. So that's not stationary. This is, and I know that because it's actually a simulated realization from a stationary autoregressive process. So whether I look at it here, or whether I look at it here, it behaves, you could say, somewhat similarly. It just looks like noise, but it isn't in fact noise. But it behaves similarly in this period to this period. So once we've decided that we can model, or once we've made the heroic assumption that we can model data with a stationary model, we can describe the correlations with a function of one argument, h. This is called the autocorrelation function, and you get it from the previous one. This was the autocovariance function, gamma h. You get it by dividing gamma h by gamma 0, and this function gives you the correlation between, well, x0 and xh, or xt and xt plus h, or xt and xt minus h, any two random variables separated by lag h. This is the autocorrelation function. This is what we've been attempting to estimate from data, and we'll come to the estimator very shortly. So what's noise? Noise informally is a process with an ACF which is always 0, except when h is 0. Obviously, just to step back, when h is 0, then the ACF is 1, gamma 0 divided by gamma 0. But a white noise, it's a process xt, which is firstly stationary, and its autocorrelation function is effectively the identity of the indicator of the event h equals 0. So this is just fancy mathematical notation for saying it's 0 everywhere apart from when h is 0. Okay, and this is white noise. So in words, it's no serial correlation. A white noise has no serial correlation. And because it's stationary, it will have a constant mean, and it will have a constant variance. And let's suppose that the constant mean is 0 and the constant variance is sigma squared. Then we would say that xt is a Wn, a white noise with mean 0 and variance sigma squared. This doesn't mean IID observations. This doesn't mean IID observations. For IID observations, we have another name, which is strict white noise. So if I say strict white noise, that does mean a sequence of IID random variables. So if you may see Wn, you may see SWN. S is for strict, and again, we can give the mean and the variance. mu and sigma squared. In this case, often we assume that the mean is 0. So this is IID and this isn't. Now, why is this important? Well, in fact, a GARCH process under conditions is a white noise. A GARCH process is actually a white noise. It's an uncorrelated process. It has lots and lots of structure, but it is a white noise. To build that up in stages, in fact, there's another idea in the textbook. So I'm doing the whole chapter in time series in an hour and a half, but there's another idea in the textbook of noise, and that is the idea of a Martingale difference sequence. So some other notation that you're going to see, actually, quite often you're going to see these calligraphic Fs, which stand for sigma algebras. And they are indexed by time, and then when we have a sequence of them, it's called a filtration. But this is a mathematical model for the, if you like, the evolution of the information about this time series, or the information that we have. So the filtration is the evolution of the information we have about the time series. As time goes on, we observe more and more observations, we learn things, and we collect information about the time series. And that's called the filtration. Or to be more particular, often we deal simply with the natural filtration, which is the one where each sigma algebra is generated by the time series up to time t. So this really just describes the information that we collect as we observe the time series. We see more and more observations and we collect this information, and this information forms the natural filtration. Of course, there are other things we might need to know. We might be reading the newspapers, so we get other kinds of information that is external to the time series. And we can also put those into filtrations, but let's not worry about that.
And for instance, if you want to model insider information, the insider will have a somewhat bigger information set because he has inside information. So everything to do with modeling information, insider information, etc., somehow mathematically can be put away in these script Fs.
Yeah. So these script Fs, we'll call FT, we'll often just call it the history up to time t. It's sort of everything we know up to time t, including the evolution of the process, sometimes mostly only the evolution of the process itself. In credit risk, we might put some other things in there that we know. But FT is the history or the information up to time t. Okay. Now, what's a Martingale difference sequence? So xt is a Martingale difference sequence. There are three things that have to be fulfilled. It should be a process where the expected value of xt is always finite for all t. Each of these random variables should be so-called measurable with respect to ft, but just look at the orange bit. This is the only important bit at this hour of the afternoon. The orange bit says that the expected value of the time series, given everything we know up to time t, is 0. So if xt plus 1 is the next observation, and ft is everything we know up to this point in time, a Martingale difference just says that the expected value of the next observation or the next random variable is going to be 0. And in fact, GARCH processes are Martingale difference sequences. They obey this condition here. And you might think, well, what's this got to do with martingales and differences? Well, there's the one-liner there. This is the Martingale property. If xt were a martingale, the expected value of xt plus 1 given ft would be xt. If we difference that process, that is, if we look at epsilon t, then epsilon t will be a martingale difference. So that's why. Anyway, this orange property is the only important thing on this slide to retain, because our GARCH processes will have this property. And you can show that if you have a process that has this property, the MGDS, and moreover, if you check that the variance is always finite, constant and finite, then it's a white noise. And so what we'll find is GARCH processes, they have this property, and if we take care of the parameter values, they will have a finite variance, and so they will be white noises. I think that's as much as I'll do there. Right. So again, in standard actuarial courses and university courses and time series, you spend many weeks studying ARMA, autoregressive moving averages. To be honest, they're not particularly useful for modeling volatile financial returns, but we can put them in there. We can use them a little bit, but they're not the most important thing. So let's just make a few points about the next 3 or 4 slides and move on to GARCH. So this is the most general definition of ARMA. You build it from white noise. So let epsilon be a white noise. So that is an uncorrelated process. It could actually be a GARCH process. But we assume it's white noise. And then xt has an ARMA process if each xt satisfies equations of this form here. So you have a linear combination of xt in previous values equals a linear combination of epsilon t in previous values. And the number of x's, that's p, and the number of epsilons that you look at, that's q, the ARMA process. And for many, as this subject developed, ARMA processes were used for modeling all kinds of phenomena and predicting all kinds of stationary phenomena, but they're not much good for volatile financial risk factors, or at least for the main features of volatile financial risk factors. I will use the word innovations. When I build a model like ARMA, starting with noise, I will call the noise innovations. If you like, these are at every time t, you get the value of the process from past values of the process, past values of the noise, and one new innovation. That's the new thing. And if you like, epsilon t here represents the news. The news is new. Let's forget about backshift operators and things. There are compact ways of writing these models involving operators. And there is a theory which I would normally spend with undergraduates about 5 weeks doing this theory. I'm trying to get through it in 5 minutes, as you can see. But because on the assumption that some of you will have seen it, it at least allows you to link your knowledge of time series to what will be a bit newer, I hope. We generally look only at causal ARMA processes. Causal ARMA processes, in fact, all can be represented as linear combinations of the noise variables. They depend on past and present, but not future noise processes. That's what makes them causal. And for these processes, these causal ARMA processes, you get a nice expression, or a relatively nice expression, for this autocorrelation function. The ACF of a causal ARMA process, you get a formula that you can calculate. And this can have all kinds of behavior. It can decay exponentially. It can look like a decaying sine curve. It can do various things. But typically with the financial returns, we won't observe the kind of behavior given by this autocorrelation function. So I really want to get to 4.1.3. I have included one dense slide which sort of gives, in a nutshell, the theory of when is the ARMA process stationary and causal. A very famous theory about when the ARMA process is stationary and causal. But the only thing I think I want to tell you about on this slide before we move on is this point here, which is that if you look at the orange sentences here, an ARMA process can be written in this form. It can be written as xt plus mu t plus an innovation epsilon t. And everything in mu t is written here in this formula. And the point is that mu t is the conditional mean of the process. So mu t is the conditional mean of the process. I'm assuming here that the epsilons form a Martingale difference sequence. That's going to be fine as long as xt is a so-called invertible process. This mu t will be ft minus 1 measurable. The important bit is that mu t is the conditional mean of the process. And mu t is given by this. So the way you understand ARMA processes is they give a structure to the conditional mean. They give a structure to the conditional mean. And so if you're wanting to predict the mean, you use ARMA processes. If you want to predict the conditional mean, that is, what is the expected value of xt given information up to time t minus 1, then you build ARMA processes. But if I'm allowed to just jump back to my stylized facts really quickly, I have this stylized fact here which says conditional expected returns are close to 0. Okay? It is very difficult to predict a log return of a stock price or an index or an exchange rate. It's very difficult. Often the best prediction is 0. I know that because they have very little serial correlation. They have very little serial correlation, and you really need serial correlation to be able to make a prediction other than 0. So, to go back to the ARMA processes.
Well, but when we look at over long time series of stocks, you basically see that they're increasing in value. So
there's
small positive.
There could be a net small positive increase over time. But looking at the daily and weekly and looking back, because we made some with R, we made some pictures. If you look at the actual estimates of the correlation between week T and week T plus 1, these are negligibly small. But yeah, over time, well, it doesn't, in my opinion, in my portfolio, they don't always drift up over time. But
I confirm that.
Okay. So an ARMA process puts structure in the conditional mean, but if you're dealing with data where your best guess of tomorrow's return is close to 0, you don't need a lot of ARMA structure for the conditional mean. You can use it, but what is going to be much more important is to model the conditional variance. And so that's where GARCH comes in. What we're going to see is that a GARCH process is basically the most natural way of modeling the conditional variance that you can think of. And so it is completely analogous to ARMA. ARMA is a set of natural models for the conditional mean, and GARCH is a set of natural models for the conditional variance. And there are nice parallels between the two that I will get into. Right. So to finish this first little half hour, when we make those pictures, of course, we plot estimates. So I told you there was a picture called the correlogram. These are pictures of estimated serial correlations. What do we actually do? We have a sample of size n. We have a sample of size n, and we estimate the correlation at lag h by forming this ratio. X bar is the sample mean. So we just compute this, and that's our estimate of the autocorrelation at lag h. And Theorem 4.1 just says that it tends to be quite a good estimate. So under some conditions, if you have a causal process driven by strict white noise, you can show that these estimates are reasonable estimators of the true values. And in fact, the covariance matrix, the asymptotic covariance matrix is known explicitly, but this is the result on which the picture is based, on which the pictures that we saw are based. So it applies in the case where, so a special case of this result is when you're dealing with strict white noise itself. So when xt is strict white noise itself, that is, when xt is a process of IID variables, we know how the estimated correlations should behave. They should be asymptotically normal. These estimates should be asymptotically normal, and the covariance matrix should be the h-dimensional identity. And this is where we get the confidence intervals from. Basically, our correlation estimates should lie between two normal percentiles with probability 1 minus alpha. And this is the interval which is shown in the correlogram. So it comes all from the statistical theory of how these estimators should behave. And so we plot the correlogram. We plot these estimates against, we plot rho hat of h against h. except that we don't tend to draw points, we tend to draw vertical bars. We call it the correlogram, and we can supplement it with numerical tests. There are a variety of tests, usually involving Box or Leung, in which you take sums of squares of these estimates and compare against chi-squared distributions, and these you use as formal tests of whether your data are independent. So the null hypothesis here is that we have strict white noise. The data are strict white noise. And under that null hypothesis, we should have normally distributed estimates. 95% of them should lie within an interval defined by these boundaries. And if we sum up squares of them, they should have chi-squared distributions. And if that's not the case, then we reject the strict white noise hypothesis. Yeah, chi-square, so it depends how many you take. So you might take, H might be 10. So you might take the first 10 lags, the estimates of the first 10 lags, something like that. And so there's one very important comment on the bottom here. If you have a time series which is strict white noise, and if you square it, or indeed if you take the absolute values, it's still strict white noise. Strict white noise is another word named for IID. So if I square it or take the absolute values, it's still strict white noise. And it's never enough just to take the data, draw the correlogram, and do, for example, the test of Leung and Box, and then to say, okay, I don't see anything in the correlogram, the test is not significant, therefore I have a strict white noise. You've always got to look at the absolutes and the squares when you're analyzing financial returns, because you may find that although the raw data pass, the absolute values and the squares fail completely to be consistent with strict white noise. Now, it's going to be much better to do that with data. So we will do that with data after we've fitted some GARCH models. Please, yeah.
There was a lot of asymptotic behavior there.
Yeah.
Enlarge. What does enlarge mean in this case?
I want me to say how big the data set should be. Yeah.
To hold the asymptotic square.
This depends on so many things. The nature of the underlying distribution, is it light-tailed or heavy-tailed? The question is, how fast is this convergence? It's all based on the speed of this convergence to normal. And that will depend a lot on what's the distribution of the underlying innovations. When I am fitting models and doing some of these tests, I'm usually working with values of n which are multiple hundreds of data. In daily data, I would quite like 2 years, which is 500 trading days. I might prefer 4 years. But as to, how quickly do these results, how quick is convergence, that all depends on, what's the nature of this strict white noise. I haven't said that the Zs are normal innovations. They could be heavy-tailed innovations. So it's,
No, that's fine.
yeah.
So it's less than 10,000 and it's more than 10.
Yeah, more than 10. I'd want more than 100 as well. Yeah. Yeah, I'd settle for more than 10,000, but yeah, I'd more than 300 or 400. What do you think, Marius?
It's a good comment.
Yeah, it's a good comment.
If you have too much data, then even the distribution you sample from will be rejected. It's one of the bigger problems in big data.
Yeah.
And too little observations, of course. Yes,
The theory doesn't work.
you
Yeah.
could probably still bootstrap it or something like that. If you don't believe in the sensitivity.
Believe in these intervals. Let's say if alpha is 5%, is Q1 minus alpha over 2, of course, it's typical to 2, or 1.96. So that's why I say this plus minus 2 square root of n gives you a very rough first estimate. But if you go more in detail, then you'll see that these better intervals are a bit more narrow in the beginning, and then get a bit more broader. So it's only very, very first order asymptotic. But they're doing fine. No, that's important. But insider is a bit like that. There are all sorts of corrections.
So ARCH and GARCH, they're actually very natural models. And it's surprising that it took probably until the 1980s for them to be invented, because they are the sort of natural ways of modeling a changing conditional variance. And, okay, it's a bit of a mouthful. ARCH is autoregressive conditionally heteroscedastic. The first two words are, well, we'll look at all of those words in turn, and the G is just generalized, but we usually start with ARCH. And I like these models because they're quite simple models, but they're going to be able to produce a lot of the stylized facts, as we will see. So Engel came up with ARCH originally, and so he said, well, let's have a process built like this. So let ZT be strict white noise. So here the building block, the innovations are strict white noise. That is, this is some independent process. Could be normal, doesn't have to be. And we will set the mean to be 0 and the variance to be 1. So what happens in an ARCH process is you multiply the innovation ZT by sigma t, and sigma t is given as basically a constant plus a linear sum of previous squared values of the process. So this is a set of equations for all t, and the coefficients here have to be non-negative. So ZT could be normal, as I've said. It could be, for example, these ZTs, quite often what we will take is a student distribution. There's a little problem with the student distribution in that in its standard form, the variance is bigger than 1, so we scale it. So you might see this quite often. This just means that we scale it so that the variance is equal to 1, so that we have a strict white noise with variance 1. What sigma t here, the way we've defined this process, sigma t is the conditional standard deviation of xt. So given the past values of the process, sigma t here will be the conditional standard deviation, and sigma t squared the conditional variance. And you can see that, how does this work? If previous values of the process are large, this will be large, sigma t will be large, and therefore the standard deviation of xt will be large, or the conditional standard deviation. Some of these remarks here. ARCH is a Martingale difference sequence. The first thing one can verify, and I'm not going to go through the mathematics because obviously it would be sort of futile. We wouldn't get anywhere if I go through all of these equations, but let me pick out, and mostly it's in color, let me pick out the key ideas. An ARCH is a Martingale difference. It has this property that the expected value of xt plus 1, given the history, that is, given all the variables up to time t, is 0. And I've said that this is a sort of stylized fact of financial time series, that your best guess of tomorrow's return is that it's 0, because you don't know if it's going to go up or go down. So it's a Martingale difference. Moreover, if it's stationary, let's assume it's stationary. Later on we give the condition. Let's assume it's stationary. Then the variance, the conditional variance, will be sigma t squared. So the conditional mean will be 0. The conditional variance will be sigma t squared. And we call sigma t the volatility. So finally I will identify the concept of volatility with something mathematical. I'll identify it with sigma t. It's changing in time. It depends on past values. And in this way, I can get the volatility clustering, because if one of the previous values is large, or several of them are large, but at least one of them is large, then xt will tend to be large. And this is what makes it ARCH, autoregressive, because xt kind of depends on previous values, like an autoregression. Conditionally heteroscedastic means a conditionally changing variance, or a changing conditional variance, something like that. Now,
how important is it, if you go to the previous slide, even a slide there before before this one. In your definition of Z, you said it's a strict white noise with average 0. If you take, as we observe for big stock indices, that there's a slight increase over time.
Yeah,
so
we're
a very small number, much smaller than the.
But we're going to deal with that in a different way. So we're going to deal with that in a different way. We're not going to change the centering of this noise. What we're going to do to model that phenomenon is we're going to add something.
Oh, okay.
We're going to add a muti. We're going to add a muti, and we're going to give that ARMA structure. So we'll have a bit of ARMA structure, even though it's not, like, let's say, a first order effect or first order importance. Now, the book takes you through the properties of ARCH. And if it's a nice theory to teach because you can calculate lots of things, you can work out the conditions for when the ARCH process is both strictly stationary and weakly stationary. They differ. And moreover, so the blue points sort of summarize it. You get a condition for strictly stationary. What you also find is that you get a heavy tail process. Even if ZT is normal, so suppose you start with ZT normal, when you build this process, you get an XT which is not normal, and in fact which is leptokurtic. So the GARCH mechanism creates heavy tails without having to do anything else. It will create a heavy tail out of normal innervations, and if you give it student innervations with quite a heavy tail, the XT variables will have an even heavier tail. And you can also show that the squared process is in fact an AR1 process. That's quite nice. This is a parallel with the autoregression. XT squared is an AR process. Now, it looks like this. That's a realization, 1,000. This is a volatile process. You don't immediately see it. It doesn't look volatile enough, if you like. If you remember the 2008 crisis, this doesn't look volatile enough, but it is a volatile process. That's the volatility. It's changing. In other words, what you see in B is the path or the values of sigma t, the conditional standard deviation. That changes all the time. When you look at the ACF, the theoretical ACF is the zero function, except when h is 0. The theoretical ACF is the zero function, so we can generate some data and estimate it, and the estimates will largely lie between the confidence intervals because this is a white noise. However, if we look at the squared values, and compute the autocorrelations and make the correlogram, we will see that the correlations are non-zero. We will see that they are significantly outside the confidence interval. That's because the autocorrelation function of xt squared is actually the same as the autocorrelation function of a first-order autoregression. So we're getting some of the stylized facts here. We are getting no serial correlation, but serial correlation of the squares. It would also be for the absolutes. We're getting some volatility, but we need to do a little bit better. So where GARCH comes in, it's just a refinement. You'll see that the only addition here is another term, and this term here is a linear sum of past volatilities. So sigma t now references past values of itself, and this creates more volatility. This structure creates more volatility. So Engel's PhD student suggested this generalization. So if previous x's are large or previous volatilities are large, xt tends to have a distribution with a large conditional variance. So the periods of high volatility tend to be more consistent. And there are beautiful parallels with the ARCH theory. You get a condition for stationary, which we won't go into. And you find out that, in fact, the GARCH 1-1 process, so the most popular model in practice is when p equals 1 and q equals 1. P is 1 and q equals 1. That's called GARCH 1-1. And that is like an ARMA 1.1 process for xt squared, which is a process that can do a bit more than AR1. Right. Yep.
In the definition, you require an ARCH process to be strictly stationary. And now we have a theory about case units strictly stationary.
Yeah, there's in a sense, it has to be strictly stationary, but that doesn't allow us arbitrary freedom about these alphas and betas. So yes, I will only call it a GARCH PQ process if it's strictly stationary, but that doesn't mean I can have, that doesn't mean that in fact I'm allowed any non-negative alphas and betas. In fact, I will have to restrict the alphas and betas, and this is the restriction. Yeah.
Then it is a GARCH process, that means it's strictly stationary if we have this condition.
Yeah, yeah. So if you have a process that is defined according to these equations, then it is only a GARCH PQ process if this holds. Yeah, yeah. Okay. Yeah. But what I wanted to do was to now show you this here. So we recommend, so this is chapter 4, obviously, and what I'll show you first is GARCH simulation, because we'll have a quick look at the stylized facts. This package is what Marius called RuGARCH or RuGARCH. I think it was written by someone called Alexios Galanos, who, it's a brilliant package. It's very powerful. It does all kinds of things. Alexios works in a quantitative trading fund somewhere in America, but somehow he finds the time to maintain this package. And it's a kind of all-singing, all-dancing package. And I'll just give you a little bit of insight into some of the things it can do, RuGARCH. So, you'll see that the package is being loaded slowly. The first thing we have to do, what I'm going to do is just simulate one of these processes. And you'll see here there's a function uGARCH spec. I can maybe drop down the documentation for this package, RuGARCH, and bring up the, you see there's lots of functions in it. That's a list of the functions in it. Well, let's look at it this way. uGARCH. uGARCH spec. Yeah. Univariate GARCH specification. So I just wanted to show you this because it gives you a sense of the level of detail in this package. So when you specify a GARCH model, you specify the variance model. And I've only talked about ARCH and GARCH. So what I've talked about in the language of this process is standard GARCH, sGARCH, but there's a bewildering variety of other GARCHs that this will do. iGARCH, eGARCH, GJR-GARCH, AP-GARCH, CS-GARCH, NGARCH, AVGARCH. So there's all kinds of variants on these dynamics. And that's the variance model. Not only that, you can have a mean model. So you can model the conditional mean through an ARMA. You can have an ARMA order. You can have a fractionally integrated ARMA model, which I've never ever used. Moreover, the innovations. You can choose different innovations. So valid choices are normal, skew normal, student T, skewed student, etc. So there's all kinds of things in here. So if you'll see on the left-hand side, what I do is I choose standard GARCH, sGARCH, and I set the order to be 1, 1. So just to be perfectly clear, and at the risk of repeating myself, I am talking about this model with P equals Q equals 1. Oh, we don't. have to make sure I go the right way. My mean model, I won't have a mean model. So that's why. So I don't have an ARMA of 0, 0. I don't have a mean model. I could have one. It's going to be pure GARCH. I will use normal innovations, and I've picked some parameter values that correspond to those constraints that we mentioned. And so I specify the model, and you can see, if I look at the specification, this is a summary of the GARCH model spec. The conditional variance dynamics are standard GARCH, and the conditional mean dynamics, well, 0, 0, 0 means there are no conditional mean dynamics. I'll come back to the slides a little bit later and just write down what it means to have a model that is both ARMA and GARCH, an ARMA GARCH. I'll come back to that, the theory of that later. Okay, so let's simulate it. So this is a nice package for simulating data which behaves a bit like financial returns. So I'll simulate 2,000 observations. I throw away some starting values. That's not really important. And I'll make two paths. I'll make two. I could have 10 paths. I could have 20 paths, each of length 2,000. And yeah, you can see that the horizon's 2,000, and I have two simulations. And a little bit of summary information. What else shall I show you? These scripts are quite detailed. One thing about this package, it uses the 4th generation of the S language. So you find, so there's some people use 3rd generation objects and some people use 4th generation objects. The 4th generation objects are a lot more complicated to understand. And when people start using for the first time, they find it difficult to work out where all the results are stored in these objects. And so there are a lot of commands here, get class, get slots, which sort of analyze the structure of the objects created. And so I won't go through all of these. But if you're wanting to kind of work out what's in them, you can work through this script at leisure. But that's the path of the volatility in my model. I am looking at, by default it gives, I made 2 simulations, but by default it's just giving me the first one. So that's the path of volatility, so sigma changes. And this one here is the process itself, so that is the GARCH 1.1 process itself. And okay, that's a kernel density estimate of the distribution of the volatility, sort of skewed to the right. I'm not sure if that's particularly interesting or not. And that's the kernel density estimate of the distribution of the time series itself. Now, even though I asked for a normal distribution for the innovations, the process itself is non-normal, as we will confirm very shortly. So, let's jump down a little bit and look at some of this. This object path contains my simulations. It contains 2 realizations, but it also contains additional information like the path of the volatility, the sigma t, as well as the xt. If I want to extract sigma t, there's an extraction function called sigma, and so I can have a look and I can see that these are the sigma values for the first simulation, and these are the sigma values for the second simulation, the first 6. And I can, yeah, I prefer that plot. So here you can see the first simulation. That is a plot of the volatility. So you see some higher volatility here and some lower volatility. So it's starting to look something more like financial data, but still not as extreme in terms of the volatility clustering. That's the second path. I did 2 paths. Now, let me jump down a bit. This is the actual data. This is the XT. This is the XT. And I'm going to now look at this question here. Does the simulated series conform to the stylized facts? Does it behave like the stylized facts of empirical finance would suggest that it should? Okay, so there are two realizations here. So I'll just take the first one. Let's have a look at the ACF. So this is the ACF, and or the correlogram, the estimated ACF, and you find what you would expect to find. The little estimates at lag 1, 2, 3, 4 are minuscule numbers, some positive, some negative, and only one of them out of 32 or 3 protrudes beyond the confidence interval. And this is supposed to be a 95% confidence interval. So it sort of looks like, so I see this, I've got some data and I see this and I think, oh, am I dealing with strict white noise? Could I be dealing with strict white noise? Well, no, because what I should always do now is I should look at the ACF of either the absolute or the squared data. It doesn't really matter which. So we look at the absolute data and compute the same picture, and you see significant correlations. So this is one of the stylized facts. This simple GARCH model, and it only had 3 parameters, incidentally, so just going back up to where it was specified, you'll see that it's made out of 3 parameters, alpha 1, beta 1, and omega. If you want to map these to the model here, well, alpha 1 is alpha 1, beta 1 is beta 1, but omega is alpha 0. Okay, omega is alpha 0. So very simple mechanism, but I create this serial correlation. And I could do the same thing. So let me, instead of doing the absolute values, let me do the squares and see what happens there. Yeah, so it doesn't matter. I do the squares, so I get the same kind of thing. Absolutes are squares. The squares of a GARCH 1.1 actually follow an ARMA 1.1, for those of you who know ARMA. Who knows what the absolutes follow, but they are, or what the name is of the model which they follow, but they show serial correlation. Now, that was the correlation. What about the distribution? Well, that's the QQ plot. Is it a straight line? I've seen worse. I've seen worse. I'll put a straight line on it. So I put a straight line on it through the point 0, 0. And there is this inverted S shape. It's not so pronounced, but the inverted S shape that we saw earlier is present. And theory tells us that these observations are not from a normal distribution. So they are not from a normal distribution. The GARCH mechanism creates heavy tails. So they really aren't from a normal distribution. I will run one GARCH test, one normality test. So I've run the Shapiro-Wilk normality test. That's done with Shapiro. I think it's in base R. You don't need any packages for that. Whereas for other normal tests, you might need some other packages. So I will just do the Shapiro test, and the p-value is very small. So what that means is that the null hypothesis that these numbers could be normal, we would tend to reject that at the 5% level and be fairly confident that we were dealing with non-normal data. And that would be the correct inference, because the GARCH model creates non-normality, even out of normal innovations. It creates heavy tails, or what we call leptokurtosis, which means longer, fatter tails and a narrower center. Okay, that was the first thing. In some of these scripts, you see rather optimistically exercises try simulating paths with different innovation distributions. So you can go back to the specification and you can change the innovation distribution, for example, to student. And then you would get more pronounced non-normalities. Well, obviously, if you're feeding it with student innovations, why should you get a normally distributed process? But you would get even heavier tails.
Same if you increase alpha 1 and beta 1.
Yeah. If you make the sum of alpha 1 and beta 1 go closer to 1, you would also get heavier tails. That is true. I don't know if you've studied these things before, but that is kind of in the theory here. There is a formula for the kurtosis, which depends on alpha 1 and beta 1. So I glossed over this point, but in GARCH 1.1, there is a formula for the kurtosis. And no matter what, the kurtosis of the process is bigger than the kurtosis of the innovations. Kappa here is the kurtosis. And yeah, so you can see that what you actually get depends on your choice of alpha 1 and beta 1. But in order that you are dealing with a stationary time series, the sum should be strictly smaller than 1. Perhaps should have said that. If you want to be dealing with a second order weak stationary process, alpha 1 plus beta 1 should be less than 1, then the variance is finite. If alpha 1 plus beta 1 is greater or equal to 1, it is in fact an infinite variance process. And we don't tend to use that case in financial modeling. We tend to work always with the case where alpha 1 plus beta 1 is less than 1. And when we fit the model to return data, that's what we tend to estimate. But the sum can be quite close to 1, but still less than it. Right. Okay, that was just a simulation, and what I want to spend the remaining sort of 15, 20 minutes doing is fitting one to data. So I talked about GARCH PQ here. Then I summarized some of the properties of GARCH 1.1. There is a slide which summarizes the properties of GARCH PQ, but we will jump over this because, in fact, in practice, the most widely used model is GARCH 1.1. So GARCH 1.1 is very commonly used, sometimes GARCH 1.2 or GARCH 2.1, but seldom anything of much higher order. So let's not worry too much about GARCH PQ. But the GARCH models effectively are like ARMA models for the squares. That's the best way of thinking of them, ARMA models for the squares. This is relevant. So this relates to your question, Frank. How do we model these mean effects? The fact that probably there is over time some tendency for the levels to go up and down. So we can combine ARMA and GARCH. We can combine GARCH for the conditional variance with ARMA for the conditional mean. And I've sort of defined the most general model here, as in the book. But basically, the thing to look at is that we set up a model like this. We have xt is mu t plus epsilon t, and we have epsilon t is sigma t zt. Zt is the strict white noise. So this is the strict white noise. The mu t bit follows a so-called ARMA specification, whereas the sigma t bit follows a GARCH specification. So the net effect of these two parts is, obviously, I have a model of this form. And so this is known as an ARMA model with GARCH errors. And this is the kind of model that RU GARCH will fit to data, an ARMA model with GARCH errors. These are quite flexible models. Mu t is the conditional mean. Sigma t squared is the conditional variance. As you saw in the package documentation, there are all kinds of other models. And one of the main features of these other models is introducing asymmetry. So particularly with price series, there's a suggestion that a large drop in the value of a price series will lead to more volatility than a large rise in the value of a price series. There's a kind of asymmetry of that form. In the basic GARCH, the effect on the volatility is the same regardless of whether it's a large drop or a large rise. But that may not be what you want in reality. So various econometricians have collected evidence where they suggest that, they call it a leverage effect for reasons I won't go into if I can even remember. Anyway, the inference is that you should have more volatility if there's a drop than if there's a rise. And so you introduce some asymmetry into the dynamic equation. This is really popular, GJR. These are three people, Mr. G, Mr. J, and Mr. R. Have a look in the first one's Gloston. I forget the other two, but it's cited in the book. And this is very popular. Threshold GARCH is also popular. So there are two ways of adding asymmetry to the model. One is this kind of idea. You introduce another parameter in the volatility equation so that the volatility reacts asymmetrically to recent values. The other is that you use an asymmetric innovation distribution. So you don't have to use a symmetric normal, you can use a skewed normal, and you don't have to use a symmetric student, you can use a skewed student. So there's two ways of putting asymmetry into the model. And my experience suggests that they both can have value. Okay, how do we fit them to data? Well, the short answer is maximum likelihood. So we use maximum likelihood. And so I will just do that. But what will happen in the script is I will take some data, I will fit two GARCH models. I will fit a GARCH model with normal innovations and a GARCH model with student innovations. And I'll try and work out which is better. And I will look at the so-called residuals as part of that. So the residuals of the model, in a GARCH model, this is the basic structure here. Okay, if we have an ARMA conditional mean term, we have a mu t, but often this is 0. And the residuals that we will be calculating are the ones at number 2 here, the so-called standardized residuals. So after we fitted the model, what we try and do is we try and reconstruct the noise. The idea is that we reconstruct the noise. So ZT hat is supposed to be our estimate of the noise. So that's the standardized residuals. And basically, we have xt. We may estimate a mu t. That may be 0, it may not be 0. We subtract that to get an estimate of epsilon t, and then we divide by our estimate of the volatility to get the residuals. And what we're assuming is that this innovation process is strict white noise. So in order to judge whether the model is good, we test the residuals against strict white noise, as you will see. So this is the one called GARCH estimation. And I'll need, I think I have everything I need here. But take the standard and poor as 500. That's the index, okay? Compute the log returns and take 4 years of them. I should probably plot that. Plot.zoo sp500.r. Okay, so that's the data we're dealing with. And it spans the financial crisis. So there's plenty of volatility there. And it's 4 years of data. So there are here, let us say, around about 1,000 values because they are daily. So the time series is of length, roughly 1,000. To fit a model, I first specify what I want. So you'll see here that I will fit a GARCH 1.1 model, but I'll put a little bit of ARMA structure. In fact, I'll take a first-order autoregression just so you see how that works. And I will first assume that the innovations are normal. So the spec goes as follows. I take a GARCH of order 1, 1, GARCH order, and I take a mean model, which is of order 1, 0. That's an AR1. There is also a non-zero global mean. A non-zero global mean. That is, in this process here, I have a mu, P1 is 1, and I have a phi 1, and Q1 is 0. So I have a mu and I have a phi 1, and I have an alpha naught, an alpha 1, and a beta 1. Those are my parameters. So I specify the model, take normal innovations, and I fit it. So the function that fits it is uGARCH fit. Seems quite powerful and fast. So I fit the uGARCH model. And when you look inside this object, it contains an incredible amount of information. And I'll just emit all that information. You'll see all kinds of numbers. All kinds of numbers. And I have to scroll up quite far to get the bits that I want to talk about. GARCH model fit. GARCH model fit. So the conditional variance dynamics are GARCH 1, 1. The mean model is ARMA 1, 0, which is a special case of ARFEMA PQD. Distribution is normal. So these are all my parameters. Mu is a global mean. AR1 is the autoregressive term. Omega is like the alpha 0. And alpha 1 and beta 1. If you sum these numbers, you will get something which is smaller than 1, but not much. So this is a covariant stationary GARCH model. So it's the usual thing. You get estimates, you get standard errors. And then we have a look to see how this looks. So in the script, we plot a few things. So, okay, so this is one plot that it gives you. There's a menu of possible plots, which you can have a look at. If you just do plot, that takes you into a menu system, and you can choose about, I can't remember, 8 or 10 plots or something. This one here shows the series and what it calls 1% VAR limits. So these are estimates of the conditional quantile of xt, both the 1% and the 95%. We'll come to how those are calculated very shortly. What I will do is add 4 pictures. So these 4 pictures here, what do we have? We have the ACF of the absolute observations. Now, the RU GARCH has its own plot, so it doesn't use the standard ones. So it uses its own kind of customized plots. But this is like an ACF plot. It doesn't have the customary bar of size 1 at 0, but the blue bars are the estimates. You can see the red confidence intervals, and you see all the estimates are outside. So lots of correlation there. The standardized residuals. The standardized residuals, if this is a good model, the standardized residuals should behave like strict white noise, because the standardized residuals are a reconstruction of the innovation model, of the strict white noise innovations. So we do the usual thing. We make an ACF, a correlogram, and we do it for the residuals. We also do it for the squared residuals. And you're supposed to see here that 19 out of 20 of these values lie within the confidence intervals. And it's, I don't know, we have 3 out of 30 outside, so maybe that's too many, and 2 out of 30 outside here. So one out of every 15 outside, it should be 1 out of every 20. So, but no obvious structure. So we have no obvious structure. In comparison with this, where we have all these non-zero correlations, when we look at the standardized residuals, it's not obvious that there's any correlation left in the residuals or in the squares or in the absolutes. But if we plot them, if we do a QQ plot against the normal distribution, we don't get a very straight line. We get something a little bit weird, with an awful lot of curvature. That's because not only is the normal distribution a bad choice, the tails are too light, but there's actually a lot of asymmetry here, as mentioned. There's a lot of asymmetry here. So upshot is this model is not good enough. This model is not quite good enough. So I go on to change the innovation distribution. So the only thing I change is I change the distribution model to student. Otherwise, the specification is the same variance model, the same mean model, but the distribution changes. And I fit that one. And I get a fit, and we have a look at we just look at the same numbers. So what's changed here? Well, the only thing that's changed, the distribution is now STD for student. And there is one further parameter, shape. So there's an extra parameter has popped up. And this, of course, is the estimated degree of freedom of the student distribution. So there's just one more parameter. And sort of mentally remember these 4 pictures. Remember these 4 pictures in your mind. And now look at these 4 pictures. Okay, so that hasn't changed. That's barely changed. That, well, okay, there's only 1 out of 30 outside now. That has straightened up a little bit. That's straightened up a bit. But there's still sort of curvature in here. And so I wouldn't be completely satisfied yet, but if I formally compare the model with normal innovations with the model with student innovations, I would say the model with student innovations is much, much better. There are a couple of things one can look at. One can look at the log likelihood at the maximum. In the student model, the log likelihood at the maximum is almost 30 bigger, which in log likelihood scales is a lot better. We could do a likelihood. So now we get into, well, how do you test formally for one model being better than another? You could do the likelihood ratio test, for example. You could test within the student model, if you like, the normal is a special case of student with an infinite degree of freedom. So you could test the hypothesis that the normal distribution is sufficient against the alternative that the t distribution would be better. So that's what I've written here, actually. So you see the annotations. The normal model is nested within, is a special case of the t model. So you can do a likelihood ratio test. If you do it, this likelihood ratio test, you get a significant result. That's the likelihood ratio test statistic. It is much, much bigger than the corresponding quantile of a chi-squared. So this is a very significant likelihood test result. You would reject the normal special case. You look puzzled, Frank.
Do you take into account that you have one extra
parameter? That's the degree of freedom here. So H0 normal innovations are good enough. Alternative t innovations necessary. We reject the null in favor of the alternative if the LRT exceeds the 95th quantile of a chi-squared with 1 degree of freedom. Yeah.
But is it really a ratio? Are you dividing?
Here,
Yeah.
I'm taking the difference of log likelihoods. So I'm taking the difference of log likelihoods, which is like the log of the ratio. Yeah. You can also do, if you know about it, the Akaike comparison. That's also, the numbers are also hidden in the results. You can find the Akaike. Anyway, what you will find is that the T model is much better, but you could do even better still. And so let me just scroll down to the bottom. Exercise. Here's 2 ways you can make it even better. You can take a GARCH model with asymmetric dynamics. That's better, significantly better. And you can make the innovation distribution asymmetric. You can also try an ARMA 1-1 instead of an AR1. All of these things, I think, will significantly improve the fit. So if you like, I've only just begun, and I'm not going to go any further, but all of that would do better. Why? So what's the whole point of doing this? We can describe the risk factors, but one thing we can do with these models is we can forecast volatility. So I've just executed a command here called GARCH forecast. So I've taken the better model, the T model, and with GARCH forecast, I've forecast volatility. So my best forecast of sigma for the next day is this. And then, in fact, this is a forecast for day T plus 2, T plus 3, T plus 4. These are forecasts of the series itself. So it's about time, I think, of wrapping up. And let me just pick out a couple of things that, so you'll probably see that there's like 4 or 5 slides left. Let me pick out just a couple of ideas in the remaining 5 minutes, and then, as I say, you'll never have to sit through an hour and a half again in the afternoon, just at 8:30 in the morning. So we use the residuals to check the model. That's an important part of the model building process. You fit it, you extract, actually number 2, what are called the standardized residuals. These should behave like strict white noise. So you check both the residuals and the absolutes or the squares, one or the other. You make correlograms. You can apply the Leung-Box test. That is actually in the model output. I didn't show it. Okay. There is another procedure which is quite common. What I did was MLE, maximum likelihood, but there's a procedure called QMLE, which is a fancy name for just using the Gaussian likelihood. So just using the case of normal innovations. That's called QMLE. Even when you don't believe that that's a good choice of the innovation distribution, there is some econometric theory which suggests that QMLE estimates of the dynamic parameters are not too bad. Okay? So some people actually do this in 2 stages. They estimate the dynamics simply using the Gaussian innovations, called QMLE. They then extract the innovations, and then in a second stage, they start modeling the innovations with the best distribution they can. That's possible, and sometimes it's quite pragmatic when you have many time series. A use of the model is volatility forecasting. And I think for volatility forecasting, really we just need to look at 2 equations. So I've jumped on to page 90. After you've fitted the model, how do you forecast volatility? Well, it's the purple one here. How do you forecast volatility? Well, you have all the data up to time t, let's say. So xt is your last observation. You estimate the parameters, alpha 0, alpha 1, and beta 1. And then what you need is an estimate of volatility on day t, which you have in the model. You have an estimate of the volatility on day t. And so by using this formula here, you get a forecast of volatility for, I've said day, but for the next time period. If your data are weekly, you would have a forecast for the next week. If your data are daily, you have a forecast for the next day. It's just the defining GARCH equation, but you replace the parameters by their estimates, and you also have to put in an estimate of the volatility on day t. And so you get a kind of recursive scheme that from the volatility on day t, you estimate the volatility on day t plus 1, and then you can use that to estimate the volatility on day t plus 2. Well, actually, it's a bit more complicated than that. The formula for the volatility on day t plus 2 is actually given here. It's a general formula for volatility forecasting. Now, final idea. There is a poor man's alternative to GARCH. which involves no estimation at all. And this is what the risk metrics group pioneered at JP Morgan originally. And it's the exponentially weighted moving average filter for volatility. So if you have a look, it's too much detail here, but if you have a look at this equation here, and now I will show you the exponentially weighted moving average scheme. Remember that, as Frank observed, alpha 1 plus beta 1 is close to 1. So the sum of alpha 1 and beta 1 is close to 1. And so look at that equation here. A very simple volatility forecasting scheme is this one here. This one here. It's a little bit unfortunate that I've put in a mean term, but we could make that 0. So if we eliminate the mu t or just set it to 0, you get a different volatility forecasting scheme. This is called exponentially weighted moving average. And it looks much the same as GARCH, except that there is no alpha 0, and instead of alpha 1 and beta 1, you have alpha and 1 minus alpha. This was suggested by risk metrics, tends to work quite well. There is a little bit of theory. It's a little bit like estimating a model called iGARCH. An iGARCH model is a GARCH model where beta is constrained to be equal to 1 minus alpha, and alpha 0 is set to be 0. So the exponentially weighted moving average model is a little bit like a so-called iGARCH or integrated GARCH. Why is it called exponential? You're not supposed to ask the difficult questions. You're part of the team. Basically because if you iterate, it's a scheme like this, and I think we removed it from the slides. It's in the book, but if you iterate this scheme, you see that the forecasts are a linear sum of weighted previous values, and the weights decay exponentially. An exponentially weighted smoothing scheme, if you iterate, I don't have time to go into it, but if you iterate this equation, you get, it involves all the past values of the process with exponentially decaying weights.
Thank you, Professor.
My pleasure. Here's the nice thing about R scripts is they run really quickly. So I just draw a picture. Maybe you can see this here. This is my final offering of the day. No, that's when I go this way. Yeah. These are different volatility estimates. The black line is GARCH, and the dotted red line is actually the exponentially weighted moving average scheme. It's pretty close to GARCH. And there is a magical choice of the parameter that was recommended by the risk metrics group, which is alpha equals 0.06. I've called the 1 minus alpha is lambda, 0.94. And so it's a simple way of estimating volatility, which has some relationship in theory to the GARCH model. We don't obviously have time to go into that, but it's described in the book and at length, and it's as well to be aware of it. I call it poor man's GARCH because it's sort of based on less of a formal model. iGARCH is a bit of a funny model. In fact, whether it's a valid mathematical model or not is debatable.
What's the advantage? I mean, if you can do GARCH.
If you can, so people would probably say, well, it's expensive to do all this estimation, and I have 10,000 or time series, and I don't want to fit a GARCH model to every one. It seems now that that's not a big excuse because you can fit 10,000 GARCH models really quickly. Yeah. But in the old days, that was an excuse.
So that was in the 80s?
Yeah. Yeah, it's in the 80s. We're here again tomorrow. But would you like to?
Can we leave this here?
What? Just one question, sorry. Yeah. 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 Yeah, you can put a confidence interval around the volatility estimates. It's not reflected, obviously, in what we've done here, but yes, you can put a confidence interval around your estimates of sigma t, or mu t if you have it. You can make a predictive interval for xt or for xt squared. You can do all of these things as well. Yeah, whether it's completely there is, I think there's enough there to work it out. It may not be completely explicit. Right. Okay, so you probably, if you've been checking the timetable of our progress, you probably realize we're a little bit behind schedule. The final hour was to have been finishing off the multivariate story in the sense of bringing together the dynamics of yesterday, time series, with the multivariate distributions of this morning by having some multivariate time series. And in fact, I will take half an hour to do some of that. It'll be a little bit abbreviated. Coppolas is so fundamental that we will be spending more time on it. On Thursday morning, we come back to Coppola's independence, and we recap some of these concepts, and we explore the world of dependent risks in more detail. But we have the elements now to talk a little bit about multivariate time series. We have the idea of ARCH and GARCH. So on this computer here, I brought up ARCH. So you remember this idea that there is a volatility, and this volatility depends on things in the past. You have ARCH, you have, if you prefer, GARCH, which has a more complicated form here. So on the one hand, we have this, and then I will bring up something. I'll switch over the view in a second when I have what I want to show you. Some of the things that Paul talked about this morning. Paul talked about this one here. Now let's see, we have so many pointers, it must be that one. We have this idea here, which was how you take, in this case, univariate normals and you make them multivariate normal. And then we went on, we made mixed normal distributions by multiplying through by a common scale of variables. So basically, I want to take the idea behind formula 16 and the idea behind this formula here. Maybe not so clever to change the displays like that, but I want to blend these two ideas. So I want to have a model which is multivariate, so it has some explicit dependence on the past, but I want to do it for a vector-valued process. So that's where multivariate GARCH comes in. Now I'm confused. I'm going to go back to this projector here. So for the last time. Let's make sure it's completely happy. And we're going to go on to the case of we're going to go on to multivariate GARCH. Actually, at this point, 386. Let's go all the way down. So this is chapter 14. So we're no longer following the strict sequence. What did you tell me it was, Frank? 386. There is a quicker trick. Go to, but sometimes one just persists with the. Yeah. So we go into multivariate time series. Now, I won't go through everything here. It's included, there's enough here that it tells a coherent story. So what is interesting simply is that it's the same as the univariate story, all the same building blocks, but just for vectors. So it starts with the story of the moments of a time series. It goes on to the idea of stationary. What does it mean to say a vector valued time series is stationary? Again, you can have strict stationary, you can have covariant stationary. And once you have established or defined a stationary process, you can begin to look at the autocorrelation function, although in this case it's called the correlation matrix function. It's a matrix valued thing in this case because we have not only correlations within time for different lags, but we have correlations across components. So we get something which is matrix valued. Now, I'm not going to go into that. I'm just going to point to this and say that we have something very similar, and I'm going to go straight to the multivariate GARCH process. Straight to the multivariate GARCH process, just dwelling on one definition on the way. We have ideas of noise in multivariate processes. We have the idea of a multivariate white noise, but what you'll need for the definitions is, what is multivariate strict white noise? Well, that is really simple. Xt is a multivariate strict white noise if it's a series of independent, identically distributed random vectors. So it's just the same definition, but for vector objects instead of, or vector valued random variables instead of scalar. So that's about as much as we need to go straight into multivariate GARCH processes, and the idea is to just show a couple of definitions and then to estimate them from data and get a feeling for what is possible. So this looks like GARCH. So I'm going to say, what's a multivariate GARCH process? You build it from strict white noise, but you're going to need something d-dimensional. By the way, we might have reduced dimension first. So we might have gone from 10,000 down to 3 or 7 or something. So let's say D is more modest, but it is bigger than 1. And so what we want to do is we want to create a process out of strict white noise by multiplying by a matrix, and this matrix will depend on the past values of the process. So it will depend on this sigma algebra here, which is constructed from the history of the process up to time t minus 1. Now, how exactly is it going to depend on the past? Well, that is the art of building the multivariate GARCH model. There are all kinds of ways we can do it, and in econometrics, many papers were produced with specifications that were more and more fancy and had more and more parameters and were more and more difficult to estimate. But I think really there's only 1 or 2 models that are feasible in dimensions higher than 2 or 3, and those are the ones I'm going to focus on. So when you have a model of this kind, I don't have a mean term here. ZT is strict white noise centered at 0. So ZT has some distribution. It could be multivariate normal. It could be multivariate student. In the same way yesterday we had normal distributions, we had student t distributions. It would be something like that. The way it's set up, the expected value of xt given the past of the process is 0, but just as we had for the multivariate normal distribution, you get the covariance matrix of xt given the past by taking at times itself, and this is what we call the conditional covariance matrix. So we have a model where there is a conditional covariance matrix, and what we have to do is we have to describe how this conditional covariance matrix depends on the past, and I will use 2 specifications. A few notes. We could add in a conditional mean term. If you remember yesterday, we had ARMA GARCH. We had GARCH for the conditional variance. We had ARMA for the conditional mean. So you could do the same. So, well, here's 2 options. This could be a constant conditional mean, or there are vector ARMA processes or VARMA processes. There's a simple one, which is sort of the analog of AR. That's a vector autoregression of order 1 when you do that. So you could do this, but I won't. For my examples, I will have a 0 mean term. And I will concentrate on modeling AT, this matrix AT, or actually effectively modeling sigma t. There is a very neat decomposition of a covariance matrix in terms of a sandwich here, delta t, pt, delta t. These are 3 matrices. So you maybe have to think about this. The delta t is a diagonal matrix containing the volatilities, the conditional standard deviations. So it's d by d, and on the diagonal it has the conditional standard deviations. PT has the conditional correlations. YP, incidentally, capital Latin P is a capital Greek rho, and rho is the favorite letter for correlation. So that's a big rho, T, the conditional correlation matrix, and then the matrix with the conditional standard deviations. So the whole art or science of building a multivariate GARCH is to say exactly how these elements depend on the past. How does delta t depend on the past? How does pt depend on the past? And moreover, you've got to do it in a sensible way so that these conditional covariance matrices always remain proper covariance matrices. You heard from Paul that they have to be symmetric and positive semi-definite. Well, let's actually make them positive definite so we don't run into problems of invertibility. So we need this to be guaranteed. For the innovations, the Z's, once again, normal or student, or indeed, as Marius has introduced them, anything spherical would do. In fact, any distribution with mean zero and covariance matrix, the identity would do in here. And I'm going to use another library by Alexios Galanos. And of course, Alexios has put in one or two options for the multivariate innovations as well. So, the first possibility that I will look at is the CCC. This was suggested by Engel. Stands for Constant Conditional Correlation GARCH. So we have a process of multivariate GARCH form where the conditional covariance matrix depends on the past, but this sandwich is simplified. The sandwich, we have delta t, but the pt will be held constant. So PT will be a single constant correlation matrix, positive definite. Del T is diagonal, it contains the volatility, and the elements will follow ordinary GARCH. So you have the GARCH equation that we revisited, and that's what we're going to do for each component series. Alternatives are, of course, possible. You can put in here any of the univariate GARCH specifications. You can have the ones with the asymmetric dynamics according to whether you have a fall or a rise in the variable you're modeling. So anything can go in here. Now, in this process, if you take the matrix of volatilities, this diagonal matrix of volatilities, if you take its inverse and you multiply it by x, and you multiply xt by the inverse, we will call that yt, and this has the effect, this operation has the effect of removing volatility. So doing this to xt in this model will remove volatility, and we will get yt, which I will call the devolatilized process, and this will follow strict white noise, but with a covariance matrix equal to this correlation matrix. So that's sort of easy to check. Mathematically from the definition that yt, these are in fact independent vectors with correlation matrix PC. So this gives a clue about estimation. This fact here gives a clue about estimation. What if we take each series one at a time, estimate a GARCH like this, and then after we've estimated the GARCH, that's equivalent to estimating the delta matrix, we then perform this operation, we devolatize, and we get yt, and then to yt, from yt we can just estimate the correlation. So that's what I'm saying here. Estimation can be accomplished in two stages. Fit univariate GARCH models to each component series, form some residuals, some devolatilized data. Of course, whether it really is devolatilized or not depends on the quality of the GARCH model you've chosen, or the quality of the fit of the GARCH models you've chosen. But GARCH 1.1 will probably do a reasonable job, and then all you have to do is estimate this correlation matrix. So that's easy to do, and the alternative is to do a big maximization of everything in one step,
which is a little more challenging. This model is very much the starting point, and from which to proceed to more complex models. And I think it's generally agreed by people who've fitted this model to data that it's not good enough in most cases. In some settings it might give an adequate performance, but it's generally considered that the constant conditional correlation is unrealistic, and that not only should the impact of news be felt on the volatilities, the standard deviations, but it should also affect the dynamic evolution of correlation, or of conditional correlation. So CCC is not really used so much. Instead, the model which is used, and the one which I will fit, is DCC, dynamic conditional correlation. Once again, I'm reciting ideas of Engel here. And so we'll fit this one with the GARCH package. So go back to 76. What has changed? Everything is really as in 76, except that the PC, we no longer have a constant PC, we have a PT. And we have to decide how PT depends on the past. And the way we do it is through this strange equation here, 77. So we have 3 bits. This is something analogous to first order GARCH, but for the correlation matrix. So there is a constant term, there is a PC, there's a constant term, and then we add on combinations of the devolatized process times itself at lag values. In effect, we are going to choose P equals Q equals 1. So just think of one lagged value. And we will also take one lagged value of PT. So we'll take PT minus 1. But by the time I add this, and this, and this, what I have in brackets here is probably not a correlation matrix. So I have this funny thing here, because when I add these 3 things up, I get something which isn't a correlation matrix. It will be positive definite. That's okay. But it will be a covariance matrix. And so I have to do this little operation that takes a covariance matrix and changes it into a correlation matrix.
So, question from a notation, those alpha and betas have nothing to do with the alpha and betas from the GARCH?
Yeah, they have nothing to do with the alphas and betas from the GARCH. It's perhaps unfortunate that these are not the alphas and betas from the GARCH. These are some new alphas and betas specifically for the correlation matrices. So I think everything here we've talked about. This is a constant correlation matrix. If you like, this is the long-run correlation matrix. Rho is an operator that just gets correlation matrices from covariance matrices. YT is the devolatized process, so dividing through by the standard deviations. And actually, it's going to be the case that these alphas have to sum to something less than 1 to get a model that doesn't explode and makes some kind of sense. Now here...
And again, it's guaranteed that these Y's are white noise, strict white noise.
No. They needn't be strict white. In this model, they're probably not going to be strict white noise. There's going to be some dependencies in them. They are just devolatized, but they're not independent in this model. In the previous model, they were in the CCC. It's a little bit tricky. So CCC is a special case when those alphas and betas are 0. By analogy with the univariate GARCH model, you can sort of see what happens. In a univariate GARCH, in fact, you have an updating equation of this form. The volatility equation can be written like this, that sigma t squared is given by the unconditional variance. You have that. There should be a square there. There should be a square there, obviously. So a term involving squares of xt and previous variances. So this is for GARCH itself. So if we compare that one and that one, you get an idea of what is happening. So you can think of, thus, in DCC, this PC, you can think of it as representing the long-run correlation structure. So how do you estimate it? Or how do most people estimate it? And how does Alexios Galanos estimate it in his R code? Well, you fit univariate GARCH models to each series. That gives you an estimate of delta t. You devolatize, you get yt hat. You estimate the long-run correlation structure by applying some correlation estimator to the yt hats. And then finally, in the third step, you estimate the parameters governing the dynamics of correlation. And so, because when you see these multi-step methods, you ask, does this give good estimates? Does it give consistent estimates? Does it give efficient estimates? And in the econometrics papers, they've been through the asymptotics and decided that is the case. We will just fit the first order model. We'll fit the first order model, p equals q equals 1. We'll do it by, the final stage, stage 3, will be done by a maximum likelihood method, or a conditional maximum likelihood method. I think this slide is not worth going through. Instead, what I want to do is fit it and then come back to a few points.